Now that we know what a higher order derivative is and how to notate them, we're going to spend some time talking about an application to a higher order derivative. Like, why might we want to find the second derivative or the third derivative? We'll actually talk more about this later in a different context, but for now we have an application to physics, in particular to acceleration. So previously we learned in section 2.3 that the instantaneous velocity of an object moving in a straight line, meaning either up or down or left to right, is given by the derivative of its position function. The position function just means the function that gives the distance or the height that the object has traveled. So in other words, the rate of change or derivative, instantaneous rate of change is what we refer to when we just say rate of change, of position or distance with respect to time is known as velocity. Velocity is, again, just like speed, except velocity has a direction associated with it. Up or right is usually positive, and down or left is usually negative. How fast your distance is changing over time is how fast you're moving, or your velocity. Similarly, we can find the rate of change of velocity with respect to time. How fast is your speed changing? Are you getting faster? Are you slowing down? The term for that, or the word that we use to describe how fast your speed is changing, is called acceleration. So if we start with a function that we'll call the position function, or height or distance, we normally call this s of t. But in our application, sometimes we call it h of t if we're talking about height, just because h makes more sense to go with height. We've seen that if we differentiate that or find its derivative, s prime of t, then we get what's called the velocity function. We're just going to call this v of t to remember that this is velocity. Now, if we differentiate velocity or find the second derivative of position, then we get what's called acceleration. And we're going to call this a of t, again, for acceleration. So the relationship between these three things, position, velocity, and acceleration, go in this order in terms of finding the derivatives. The key idea here is just to remember that the derivative, which we have really straightforward tools to find for any given function, tells us how much a function is changing, or how much the outputs of a function are changing with respect to the inputs. So this is just a special case where when we have this relationship that our initial function, again, gives us position or distance, then the derivatives and the second derivative have a special meaning, a physical meaning, which is very useful for us in understanding the world around us. So let's look at an example. In example 1, we have a ball thrown upward from the top of a 160-foot cliff. The initial velocity of the ball is 48 feet per second, and therefore, because of what we discussed in section 2.3, the position function, or height, is s of t equals negative 16t squared plus 48t plus 160. Now remember that this 48 comes from the initial velocity, and this 160 here comes from the initial position, or the initial height. The negative 16, as we'll see, has to do with acceleration due to gravity. So in part A, let's find the height, velocity, and acceleration at 1 second. So the height at 1 second is just going to be given by the position function, evaluated when t is equal to 1. So we'll just plug a 1 in for the variable t in our equation. So this comes out to be 192. Now this is a height, so this will just be measured in the distance unit of measure, which in this question is feet. So it's either, it's above the cliff here, maybe it is still on its way up, and maybe it's still on its way down. We don't know. There's really two points in time when the height's going to be maybe 192 here. The velocity is going to tell us whether the ball is still going up or if it's on its way down yet. So to find the velocity, we will just find the first derivative of the position function. We have to find the derivative without plugging a 1 in first, because if we differentiate s of 1, we'll differentiate 192, and that's just 0, and that doesn't make any sense. So we'll differentiate this function here with t's in it, then we will plug in t equals 1. When we find the derivative of negative 16t squared, that will give us negative 32t to the first. Then we'll add the derivative of 48t, which will just be 48, and then we'll add the derivative of 160, which is just 0. So now we can plug in 1 for t. When we substitute in a 1 for t, we get positive 16, and this is a rate of change. It's the change in distance over time. So this will be the distance measure, which is feet, and the time measure, which is seconds. Now, because this is positive, this means that the ball is still going up. If we got a negative velocity, then this would mean that the ball was on its way down at 1 second. But we can see here that still at 1 second, the ball is rising in its height. The height is increasing at that time. Now, to find the acceleration, we just have to remember that acceleration, which we can call little a of t, is the derivative of velocity, or it's just the second derivative of position. Now, we already found velocity, so we'll just differentiate that, again with t's in it. So the derivative of negative 32t is negative 32, and the derivative of 48 is 0. So the acceleration is just a constant function of negative 32. Now, when we substitute in a 1 into the acceleration function, there's no t's here. It's just negative 32 all the time. The units for this are going to be feet per second, which is the output measure. We are differentiating velocity. Velocity is measured in feet per second. And then the input measure is in seconds. So this will be feet per second. Or we normally abbreviate that to be feet per second squared. I like to think of it as feet per second because squaring seconds doesn't really make too much sense. So here we see that the acceleration is constant, right? No matter what we plugged in here, no matter what time we were looking at, we would actually get negative 32 every time. So this is the acceleration due to gravity. There's nothing acting on this object to make it, speed up in the way that it's going downward. There's nothing pushing on it. The acceleration, the only thing that is causing the ball to fall is just gravity, which is acting on it. And that's why we get a constant function for an object in this kind of motion where it's just kind of in free fall. Now in part B, we want to find the maximum height that the rock reaches. Now, in that picture over here, we can see that the maximum height is going to be right here. This is the maximum height. It's clearly above 160, right? It goes up and then it sort of turns around and starts falling again. In order to find the maximum height, we have to know the time, right? We're looking for the height, which is given by s of t here, but we have to be able to plug in a time value in order to get the height out. So we have to consider what is happening at this point. Do we know anything about anything at this point in time? Well, like I said, we do know that the ball kind of turns around, right? It goes up and then it starts to come down right when it reaches its maximum height. The height is increasing and then the height starts decreasing. The velocity is positive, and then the velocity is negative. So right when the velocity changes from positive to negative, there has to be a point where the ball is kind of just stopped at one instant in time, where the velocity is actually equal to 0. So if we find what time the velocity is 0, that will give us the time that the ball reaches this maximum height. And then we can take that time and plug it into our height function to find the actual maximum height. So let's write that down in some math symbols. Okay, so just to summarize this, the maximum height occurs when, again, this will be a t value, when the velocity is equal to 0. So if we take our velocity function, our v of t function, which was negative 32t plus 48, and we find the point when this is equal to 0, meaning we're going to set this whole equation equal to 0, then we can solve this for t, and we'll get the time when that happens. So if we do a little bit of rearranging, there's only one t here, so we can isolate the t, maybe by adding 32t to the other side, and then dividing by 32. We'll get 48 over 32. This is 1.5 seconds. So just half a second after the point we analyzed in part A, the ball reaches its maximum height. Now, again, this is the when, right? This is the t value, but we have to find the height. So we're going to take this time and we're going to plug it into the position function or the height function. So that's negative 16 t squared plus 48t. Again, we're plugging in 1.5 into this to get the height that goes with that time. Okay, and this comes out to be 196. Now this is height, right? So this is measured in the distance measurement, which is feet in this example. So the maximum height, again, that this ball reaches is 196 feet, which again is just a little bit higher than what we found in part A, which was 190 right here at 1 second. Half a second later, it's up here at 196. Now the question in part C is kind of a review. We've done an example like this in section 2.3, where we're finding the velocity with which the rock strikes the ground. So now the place that we're going to be analyzing is actually right down here, right? This is when the ball hits the ground. So we want to find the velocity at this point. We, again, don't know how long it takes for the ball to get here. We do know how to find the velocity by finding the first derivative again and plugging in a time, but we need the time that it takes for the ball to hit the ground here. So in this situation now, we're going to be using the initial position function, the height function, and find when that is equal to 0. Not the velocity, but the height. And again, we're going to find the when, or the t value, and when the height is equal to 0. So if we set our initial s of t function equal to 0, we'll get 0 equals negative 16 t squared plus 48t plus 160. Now to solve this here, we have something to the second degree. We've got a t here and a t here. We have to either use the quadratic formula or factor. And I think that every single term here is a multiple of 16, so we can factor this. This will give us t squared minus 3t minus 10. If we factor further this quadratic here, with the 1 in front of the t squared, we can just look for two numbers that will multiply to negative 10 and add up to negative 3. And those are going to be negative 5 and positive 2. Now we're going to set each of these factors equal to 0. This negative 16 doesn't matter. We can actually divide both sides by it. There's no t there. This second factor here will give us t equals 5. And the third factor here will give us t equals negative 2. Now because of this situation, we can ignore the negative 2. In general, this would be a solution, but because t equals time, we're just going to take the 5 seconds. Right now, we're going to find the actual velocity at that time. So now we're kind of using the opposite relationships here, where we're going to take the time we found from the height, and we're going to plug this into the velocity. And just again, the velocity was the derivative of the position function, which was negative 32t plus 48. So we're going to plug in a 5 into this formula, and we'll get negative 112. And again, this is a rate of change. So the units for this will be feet, the distance measure, and then per second, the time measure. Now this makes sense that the velocity at this point in time here is negative because the ball is going downward at that point in time. And then the formula just gives us the actual value of 112. That's how fast that the ball is moving at that point in time. Now, although the acceleration exerted on a falling object is pretty much constant near the surface of the Earth, it changes a lot as you move out in the solar system, meaning on different sizes of planets, you've got different gravitational constants. Larger planets have a much greater gravitational pull than smaller planets or the moon, for example. In example 2, let's go to the moon and compare the acceleration due to gravity on the moon versus Earth. So in example 2, we've got an astronaut standing on the surface of the moon, and he or she throws a rock into the air. The height function now is given by s of t equals negative 2.7 t squared plus 27t plus 6, where t is measured in seconds. Now, the meaning of each of these numbers in this formula here are the same as in the previous example. This 27, positive 27, is still the initial velocity. So the rock is thrown upward with an initial velocity that's a little slower than on our previous example, which was 48. And the 6 is the initial position or the initial height. And this should make sense. Maybe the person must be 6 feet tall, or maybe when they release the rock, then their arm is 6 feet above the ground. So to find the acceleration for this function here, remember that acceleration is the derivative of velocity, or the second derivative of position. So first we have to go in order. So first we have to find the velocity function. This will be the first derivative of position. So we'll differentiate the given function. Negative 2.7 times 2, just bringing this 2 down and multiplying, will give us negative 5.4, t to the first. Then we'll add the derivative of 27, t, which is 27. Then we'll add the derivative of 6, which is 0. And now we want to go one more time and find the acceleration function. So here we're going to take the derivative of velocity, or again, the second derivative of position. So when we differentiate our given function for velocity here, we'll take the derivative of negative 5.4t, which is negative 5.4, and then we'll add the derivative of 27, which is 0. The acceleration is still constant, but gravity acts differently on the moon, right? There's a kind of different relationship on gravity on the moon versus on Earth. So let's compare how the gravity on Earth is versus on the moon. So on Earth, we just decided that in the previous example, the acceleration is negative 32 feet per second squared. And on the moon, we just decided that the acceleration is negative 5.4 feet per second squared. So if we kind of just determine, what is the relationship between these two things, maybe we could find the ratio, like how much more is the acceleration on Earth versus the moon. So if we divide these two, we get approximately 6. So in other words, acceleration due to gravity on Earth is approximately 6 times stronger than that on the moon. This means that it will take something a lot longer to reach the ground when you drop something on the moon versus on Earth, because there's less of a force acting downward on it. All right, in example 3, we're going to investigate what happens to velocity and acceleration in an automobile as time goes on. So here we have a velocity function v measured in feet per second of a certain automobile starting from rest, given by v of t equals 80t divided by t plus 5. We're going to find what happens to the velocity, which is, again, already given to us here. This isn't position. We already have the velocity function. This is already the derivative of position up here. We just don't know what it is, and we don't actually need it or care in this example. Okay, so in part A, let's find what happens to the velocity as time increases without bound. Now, increasing without bound, time increases without bound. Remember back from our asymptote section, or our limits at infinity, what this means is we're going to look at the limit as t goes to infinity. As time goes on, what happens to the velocity? Does the velocity go to infinity? Does the car eventually just speed up and up and up and up until it's going infinitely fast? Or does the particular car in this example sort of level off to maybe like a cruising speed of some kind? So all we need to do here for part A is look at the limit as t approaches infinity of velocity. Or in other words, the limit as t approaches infinity of 80t over t plus 5. Now remember, when we're finding limits as x or t in this example approach infinity, only infinity, all we need to do, because we're looking in the long run or at a horizontal asymptote, we need to just compare the highest degrees in the top and in the bottom, which in this case is 80t and just t in the bottom, 1t, both t to the first, and just ignore everything else. So this is approximately the same as the limit as t goes to infinity of 80t divided by t. Right, we can cancel the t's. This will just leave us with the limit as t approaches infinity of 80. And there's no t in there, so of course that this is just 80. This is a limit of velocity, so this will be 80 feet per second. Now this is about like 55-ish miles per hour. So this car starts from rest and then slowly increases its speed and eventually just kind of hovers, getting closer and closer to around 55 miles per hour. Now we could also make a table. I haven't gone too far out. I've gone in just a minute here, 60 seconds. But we can see that this car is speeding up pretty quickly. After 10 seconds, it's going 53.5 feet per second. Another 10 seconds later, at 20 seconds, it's going 64 feet per second. And as we go on, we can see that after 60 seconds or 1 minute, it's going about 74 feet per second. Now, if we wanted to find this limit by looking at a table, we should probably plug in much larger values for t, but this is where this process of finding the limit algebraically this way can help us give a more exact answer. Now let's take a look at what the acceleration is doing as time increases without bound. Again, we want to take the limit as t approaches infinity. But this time we're going to need to find the acceleration function, which is going to be, again, the derivative of velocity. Now, to differentiate our velocity function, let's take a look at it up here. It has variables up top and variables in the bottom. We can't avoid using the quotient rule in this case, because even if we bring this denominator stuff up to the top, we will convert our quotient into a product, which will then require the product rule. I generally don't recommend converting a quotient rule into a product rule. You'll have to deal with a lot more negative exponents, and the quotient rule just puts something into a fraction for you right away. So here is our quotient rule. We need to identify the numerator and the denominator. So of course here is n and here is d. Then we need n prime, the derivative of the numerator, which will be 80, and we need d prime, the derivative of the denominator, which will be 1. Putting this together into the quotient rule gives us bottom, t plus 5, times the derivative of the top, which is 80, then minus the top, 80t, times the derivative of the bottom, which is 1. Then that's all divided by the denominator squared. Now we're going to want to find what's going on with this in a limit. So let's simplify. We should probably distribute this 80 into the parentheses here, and then we can ignore this times 1, and those parentheses are on the second part. So this will give us 80t plus 80 times 5, which is 400, and then we have minus 80t. Then that's all divided by t plus 5 squared. These 80t's are going to cancel out, and what we're left with is just 400 up top and t plus 5 squared in the bottom. Now we want to find what's happening to the acceleration as time increases. So let's look at the limit now as t goes to infinity of 400 over t plus 5 squared. Now it's hard to see here, but if you were to think about FOILing this out, we would get a t squared in the bottom as our highest degree. I don't really care what's beyond that, because remember, with a limit at approaching infinity, we just compare the highest degrees top and bottom. So I'm just going to say, okay, well, this is approximately the same as the limit as t goes to infinity of 400 over t squared. Now, when we have a bottom-heavy fraction like this, then the limit as you approach infinity will always just be 0. This is acceleration, so this will be feet per second squared. Now, how does that make sense? All right, our velocity is limiting off towards 80 feet per second. Why should the acceleration be 0? Well, if you look at the increases in velocity here, right, the change in the velocity, it was pretty big at first in the beginning, but then it's starting to have smaller and smaller changes as we go up every 10 seconds. So if we include an acceleration kind of row here, let's see what happens at these given time values for the acceleration. So as the velocity levels off towards 80, then the rate of change of that will level off towards 0. Right, this is kind of like a horizontal asymptote of the graph of the velocity function. And as you approach a horizontal asymptote, the graph levels off and its slope approaches 0. In this context, that would mean that the acceleration is approaching 0. Now, just to contrast this with the previous two examples, here we are not talking about acceleration due to gravity because we're not in a car that's just free falling. This car has a pedal on it that can cause its acceleration to change. So be careful to generalize that idea with acceleration being constant due to gravity. That is only in a free fall situation. Here we have different accelerations at different times, and then in the long run, over a long period of time, the acceleration will approach zero.